This rock is the backbone of the global iron industry. It's called Banded Iron Formation, and it's responsible for most of the iron we're mining today. But here's what I think is more interesting. This rock is extinct. Many of the rocks you can find around you today are still forming somewhere on Earth. Lava is cooling into basalt, sand is slowly being compressed into sandstone, but with the way our planet is now, banded iron formation can't form anymore. In that way, it's extinct. And honestly, I'm glad. It's story time. I have wanted to make this video since very specifically the day before I moved to Michigan's Upper Peninsula, which was in December 2020. Almost 4 years ago. But there's a reason it's taken me this long. Here's what happened. In 2020, I was living in Ann Arbor and was just getting interested in geology. And I came across this article talking about a boulder on the University of Michigan campus that I know I walked by dozens of times as a student without ever paying attention to it. Like, for an entire summer, I rode my bike to work straight past this thing without ever knowing it was there. So the day before we moved, I headed down to campus and was just charmed by this thing. I mean, it was a little covered in bird poop, and hey, I wasn't at my best in 2020 either, but check out these layers. I had so many questions about how something like this forms. And what especially caught my attention was that while banded iron formations are found all over the world, this boulder had come from near Marquette, Michigan, which was about to be my new neck of the woods. So this should have been one of the first videos I made when I started this series. Here's where things went wrong. When I'm writing these videos, I rely on a number of what, historically, have proven to be credible sources. Journal papers written by scientists, websites written by professors, exhibits at national museums, that sort of thing. Well, by summer 2023, I finally had an outline for this video. I'll admit, this topic took me longer than usual to wrap my head around, so there were definitely some starts and stops, but finally, I had an outline. And then I made what turned out to be one of the best decisions I could have made for this project. I emailed Dr. Bill Cannon. What have you? I see why people come up here.
Lots of people do. Just look at it and they never look down. I always want to tell them, look at that stuff you're standing on.
Right. If you've watched this series for a bit, you have probably seen Dr. Cannon. He's a scientist emeritus with the US Geological Survey and has been studying the geology of Michigan's Upper Peninsula on and off since the 1960s. I have now lost track of the number of times I have looked up a paper about Michigan's geology and found him listed as one of the authors. So I asked Dr. Cannon if he'd be willing to read my outline and suggest any corrections. And after reviewing it, his response was essentially, "We should talk on the phone." Here was my problem. Early on in my research, I had come across a couple of sources that are usually very credible that gave very similar explanations for how banded iron formations formed. And it went something like this. Once upon a time, about 2.5 billion years ago, Earth's atmosphere had much less oxygen than it does today. During that time, there was a lot of dissolved iron in the oceans. Then, microbes started doing photosynthesis for the first time and ultimately filled the air and water with oxygen. And that oxygen reacted with the dissolved iron to make iron oxides. Iron oxide particles fell out of the water and created what would become a layer of iron-rich rock on the seafloor. The problem was, those microbes eventually made so much oxygen that they poisoned themselves, and a bunch of them died. Oxygen levels went down, and those iron oxides stopped forming. The rock that formed on the seafloor was now low in iron. Over time, though, the microbe population recovered, and this whole cycle kept on repeating. Now, parts of this explanation are pretty well accepted by the scientific community. Like Earth's atmosphere was once low in oxygen, and that did change with the arrival of photosynthesis. This is usually called the Great Oxidation Event. And it did kill a bunch of microbes because too much oxygen was toxic to them. But when it came to banded iron formations, my mistake was not digging any deeper than this. I already knew about the Great Oxidation Event, so this made sense to me, and I made the error of assuming that this must be the generally well-accepted explanation. But after 10 years of writing science videos, I should have known better than that. It's important to always check multiple sources, and especially check if there are credible, contradictory ones. And because I didn't do that at first, I missed out on something really cool. That in reality, these rocks are mysterious and not well understood. And in part, that's because they don't follow one of the fundamental principles of geology. I'll tell you more of what I mean by that in a minute. But for now, here's what happened. Dr. Cannon reviewed my outline, made some generous corrections, and then we agreed to meet up near Marquette the next time he was in the area. And that brings us to May 2024.
We're standing here on a feature known locally as Jasper Knob, a popular place for locals and tourists to come, not to look at the rocks, but just to look at the view. We're looking over the city of Ishpeming, Michigan, which was one of probably the major iron mining town on the Marquette Iron Range, which is a long belt of iron-bearing rocks. But if you look at some of this undeveloped area here, these are over old mine workings. There were literally dozens of old mines, mostly underground mines. Ishpeming is still based mainly on mining, but now only the single large Tilden mine just off to our south here is the only active mine. From a geological standpoint, Jasper Knob is arguably the most famous geological locality in the Lake Superior region, and I would be one of the ones that argue that it is. I've been here, I'm sure, at least 100 times personally, and I've brought hundreds of people here, from a small group to busloads. I've probably brought somewhere between 500 and 1,000 people here just to see this.
So you're part of the reason it's so famous.
Well,
you keep dragging people
many,
here.
many other people come here for over a very long period of time. So the rocks we're standing on are something called in general a banded iron formation, which is a very descriptive term. It means it's an iron-rich rock and it's banded, which we can see in a number of places as we walk around the outcrop here. And generally the banding is a layer of silica, commonly called chert. If it's red, it's called jasper. Then the intervening bands are some particular iron mineral. Here, that iron mineral is hematite, which is a nice shiny silvery, so it makes it especially spectacular here.
Yeah, wow. At this point, I will briefly note that Jasper Knob is an example of a superior type banded iron formation. There are a couple of other types that formed in different environments and tend to be smaller deposits, but unless I specifically say otherwise, we will be talking about superior type banded iron formations for the rest of this video.
Okay, so here's a nice rock face showing this banded iron formation. This particular type is called jasperite because it has these reddish layers are the jasper beds. Iron formations in general, they are common around the world. That's sort of the backbone of global iron ore production. And in the U.S. right now, virtually all of our iron ore production comes from banded iron formations. One mine here, there are many mines in the Mesabi Range in Minnesota from a unit which is probably the exact equivalent of this rock. It's quite likely, not proven, but quite likely that the whole Lake Superior region was mantled by a single layer of banded iron formation, 1.85 or 1.9 billion years ago. So this was being deposited more or less the same time that iron formations, say in the Gogebic Range or in the Mesabi Range, were being deposited. So it was a vast sheet of material that was being deposited on an ocean bottom, and everything in here pretty much was dissolved in ocean water and then precipitated out of ocean water and built up as various layers over time. Of course, we've been mining this material for well over a century. Earth scientists have studied it intensely for that whole time, and there are still lots of mysteries about it, which makes it kind of intriguing.
And about how old do we think this formation that we're standing on is?
We only have one data point here on the Marquette Range, and it's from a rock that was sampled in the Tilden mine just over the hill. The iron formations here, in addition to being this interlayering of iron silica, have a number of magmatic injections into them, sills. They're sort of injected parallel to the layering. They're very different. They're kind of dark magnesium iron-rich rocks. And there was one sample that was studied from the Tilden mine that someone found datable material in them, and they dated that at about 1.89 billion years old. So that means that most of the iron formation had to have been deposited here before 1.89 billion.
Right, okay.
It doesn't give us an exact time, but it gives us a rough idea.
And you said this was all forming in the ocean, so this would
It's
have
all
been
forming on the ocean bottom.
cool, underwater back then.
One of the mysteries based on the fact that iron formations on this massive scale stopped forming about 1,850 million years ago. So there's no modern analogs of this. One of the maxims in geology is to understand something in the past. You can look at something in the present, but because there's nothing analogous to this anywhere in the world anymore, we can't look at that and say, "Oh, that's what happened here."
Huh.
So, kind of speculating about it.
Brief pause. This principle Dr. Cannon just mentioned is called uniformitarianism. It's sometimes described as the present is the key to the past. And it's been a guiding light in geology since about the 1830s. Uniformitarianism is the idea that the Earth changes in slow, uniform ways, and that the processes that are happening today are the same ones that happened in the past. This means that you can use what's happening in the present to interpret things that happened millions or billions of years ago. For instance, if a geologist found evidence of an ancient volcanic eruption, they could look to modern volcanoes to try and understand what happened long ago. Because according to uniformitarianism, the sort of mechanics of volcanoes have always worked this way. The same thing goes for things like erosion, earthquakes, and how mountains form. You can use the processes of the present to try and understand the past. And usually, this is true. This is one of the foundational principles of modern geology. But I did say usually, and banded iron formations are one of the exceptions. They don't seem to have formed in hundreds of millions of years, and they haven't formed on a massive scale in nearly 2 billion, which suggests that whatever processes made them aren't happening anymore. There also aren't really modern rocks that we can use to draw good comparisons. And all of this has made banded iron formations hard to understand, especially because they seem to have formed in some complex conditions.
The issues are, first of all, you have to have a lot of iron dissolved in the seawater to precipitate out. You have to have lots of silica in the seawater to precipitate out. And I think one of the things that's kind of counterproductive when we think about this is that people consider banded iron formation as one kind of rock. It's actually two very distinct kind of rocks. So if we look at the jasper layer, this is almost entirely silicon dioxide, SiO2. So here we have a layer representing a time when the ocean floor was depositing silica. And it's followed by a time when the ocean floor was depositing iron. Another time it was depositing silica. So these are really, you should think of them as two different rock types that are just very closely interlayered, layer after layer. And it means that the conditions on the ocean floor were fluctuating dramatically from a time when you were depositing the silica layer to the iron layer to the silica to the iron to the... And this happens thousands of times over tens of millions of years.
Huh.
So it's a really remarkable thing about it. And I think not enough thought has been given to what this interlayering means. Some people a long time ago speculated maybe it's seasonal. Perhaps this is a winter layer, summer layer, winter layer. That is orders of magnitude the wrong timing.
Yeah, sure.
So it would mean that the whole iron formation was deposited in, I don't know, thousands of years or something, and it's tens of millions of years. Yeah. So that doesn't work. But we really don't know why we're having this repeated fluctuation, making rock type A, rock type B totally different, back to A, back to B. So one of the mysteries about it.
Now, of course, there doesn't have to be just one explanation here. Like I mentioned earlier, that different types of banded iron formation formed in different environments. Also, the oldest banded iron formation of any type is around 3.7, 3.8 billion years old, way older than the roughly 1.9 billion year old Jasper knob. So it's likely that there were different mechanisms at different times and maybe even in different places. In any case, not all banded iron formation is as beautiful as the outcrop at Jasper Knob, even the superior type ones. A couple of years ago, I met up with Dr. Cannon at a different site, maybe a 20-minute drive from Ishpeming, and that banded iron formation was nothing like this.
Probably one of the more spectacular things here at Jasper Knob is that these iron formation layers, which originally were horizontal flat-lying layer on the ocean bottom, now are contorted into this very complicated folding structure, which you can see. Where can you see it? Maybe not so good right here. So here's a nice example of this very tightly folded structure. You can see the Jasper layers are bent around like that. Some of these come here, bend around. If you think of a flat-lying sheet of paper sitting on a table, you compress it together, it will begin to form into these folds. So that's what's happened to these rocks a very long time ago. And there are two geologic events that both of which probably played some role in making these folds. There was an earlier one about 1830 million years ago, in which the whole region was compressed in a north-south region. And then about 100 million years later is actually when the Marquette syncline, the Marquette Trough, formed as blocks of older rocks on both sides rose up. Then these were again compressed the second time into that. And that's that two periods of folding that make this very complicated fold pattern that we see here.
And then is one of the mysteries about this, I've heard this described as like an extinct rock, because it's not forming anymore. Is one of the mysteries why exactly it stopped forming, or do we have any ideas about that?
Well, you know, as I mentioned briefly before, one of the peculiar things about this banded iron formations on this scale is that they were quite common around the world up until about 1,850 million years ago. And then they have been very rare since then. There's a few very specialized geologic situations you might form some of them. But this great mass, kind of a global period of iron formation deposition ended at that time. So there's several explanations why that might happen. One is that there's something called the Great Oxidation Event, which kind of coincides with the evolution of photosynthetic microorganisms. And they begin to oxygenate the atmosphere and the water. And to dissolve a lot of iron in water, it has to be relatively reduced. So if it becomes oxidized, you can't have large amounts of iron dissolved in the seawater. It's possible that the Earth just became too oxic. And myself and a colleague have proposed a while back, hasn't been very well accepted, that it may have something to do with the Sudbury meteor impact, which was a major impact event that truly modified things on a global basis. So perhaps something related to that is what made some fundamental changes, actually maybe to the nature of primitive life. So there's kind of a remarkable coincidence in time between the Sudbury impact event and the end of banded iron formations. But it may just be a coincidence.
Regardless of what happened, one thing stands out. Although banded iron formations used to be common and once formed over huge areas, they don't seem to be forming anymore. And based on most research, they can't. They seem to require water that's low in oxygen, because that water can hold a lot of dissolved iron. If there's too much oxygen, then the iron quickly reacts with it and just falls out of the water close to where it entered. There's no cycle, no opportunity for the dissolved iron to just sit in the water while those other layers form, and therefore, there are no stripes. And well, today, the air and the oceans are full of oxygen. So while iron-rich sediments can still form, the banded part isn't happening anymore. Banded iron formations are extinct. And yet, they're still so relevant. Banded iron formations make up more than 60% of global iron resources and are responsible for most of the iron that's being mined today. And this is what gets me. From vehicles to appliances to buildings, my modern life depends on iron and the steel we make from it. your life probably does too. And as it turns out, most of that iron is coming from an extinct rock geologists don't quite understand. I really enjoyed working on this video, and special thanks to all of the folks who support this series on Patreon and Buy Me a Coffee for making it happen. And thanks to you for being here. If you enjoy these sorts of geology stories, I am always thinking about new ones, and you are welcome to subscribe if you want to follow along. And as always, thanks for being here. I hope you learned something that makes you think about the world just a little differently, and I'll see you soon.